In this video, I actually want to talk about something called dynamic memory management. But before I come to that, I think that I should review a few things about the control flow of a program, about global and local variables, things that we already know how to use, and we also got already a bit of technical understanding for that. But for understanding this concept of dynamic memory management, what it can be used for and what you have to be aware of, we have to dig in a bit deeper. So let's begin with this example. And here, the fact that this variable b is not initialized should actually catch your eye. Because I often mentioned that if you have uninitialized local variables, the initial value of this local variables is undefined. But it was about local variables, uninitialized local variables. For global variables, this is actually not true. Global variables are always initialized. And if you don't specify an explicit initial value, the default initial value will always be 0. So you also could have written here this equals 0 initially. Now I will show you on the next slide why this is actually making sense. For that you actually already need some technical background understanding, but let's come to that back later. Let's first go through this program. Let's follow the control flow. So the control flow starts with function main, and when we enter function main, this local variable c gets allocated and it gets initialized. And it gets initialized with the sum of a and b, and because b by default is 0, and this is defined behavior, the initial value of c will be 2. Then here we call function foo, and we pass c as argument to function foo. That means foo gets a copy of this variable with value 2. Then in function foo we call function bar, and here we pass y as argument to function bar. That means bar receives a copy of this argument with the value 2. And then the return value of function bar therefore will be 4. That means when we come back to function foo and look into this expression, its value will be 5. And then we return to function main, and the return value of foo therefore is 5, and this value gets printed out. So this was a quick walkthrough without being too technical, I hope. But now I want to actually go here into the technical details, how the stack is used for the function calls, but actually a bit more. And actually I want to start with what happens when you type in the name of the executable and hit return before the execution starts. So in between, starting to run the program actually happens in two phases. First, the program gets loaded into memory, and then the execution starts. And here I first want to begin with what happens when the program gets loaded. Now for keeping things simple, I actually want to be concrete. Let's assume, for example, that we have a memory with a size of 4 GB. 4 GB would mean that we would have here a size of 2 exponent 32, so 2 exponent 32 memory cells. And then I also don't want to talk about something called virtual memory, or how actually an operating system is involved in the whole process. We assume that this program, for example, runs on something like an Arduino, where we do not have an operating system, and this makes things a bit more simpler. Now this executable, Aout, contains the program that we have written in form of machine code, what the compiler generated for us. So this executable contains machine code for these functions, for function bar, for function foo, for function main, and then in general also for some, you could say, hidden function, some startup function, which is usually called _start. And this function _start is actually called first when the execution begins. And this function start then calls main. we come back to that later. So when this executable gets loaded into memory, you can think of it that one block in memory will be initialized with the machine code for this underscore start function. Another block with the machine code for function main. Another block for function foo. And a block for function bar. And then this region of the memory will be called text segment. I simply call it text. Then the executable also contains information about the global variables. And that means about these two variables. And here we actually can distinguish between initialized and uninitialized, or not explicitly initialized variables. This variable here is explicitly initialized, and that means the executable contains the information that 4 bytes with the initial value of 2 are used for a global variable named A. And this means when the program gets loaded, some block in memory, some memory location initialized with the value 2 will be used for variable A. And another block will be used for this uninitialized global variable. The executable contains also the information that 4 bytes are required for variable B, which is not explicitly initialized. And that means when the program gets loaded, we also have this memory location. And now we can talk about how this not explicitly initialized global variables actually do get initialized. There are actually different possibilities, depending on whether you have an operating system or not. If you have an operating system, then the operating system is basically loading this executable from hard disk into memory, and then the operating system could initialize all the uninitialized global variables with 0. Or if you run a program on a microprocessor like an Arduino, then this start function might contain some code which is initializing this global variable B. This function start, as I said before, at some point will call function main. That means inside of here we have some instruction which jumps to the first instruction in function main, and before that call instruction or jump instruction you might have this initialization code. Now here I also want to introduce some terms for how to distinguish these parts in memory. The region with this initialized global variables is called the data segment. I simply call it data, and this block with this uninitialized global variables is the so-called BSS segment. Now when you look at this picture, this is certainly not true to scale. I mean, this whole thing here, the text segment, the data and BSS segment, just requires a few bytes in this example. And we have in total 4 gigabytes here. That means this part of the memory is almost 4 gigabytes large. So most of the memory is unused when we start the execution of the program. Let's hide a few details, for example, details about the text segment, that it contains machine code for all these different functions. And let's walk through the program execution once again. And with that, I want to give you an idea how the remaining part of the memory, the so far unused part of the memory, is used for this function call stack. Now, when we say the program execution starts, it actually means that the first instruction in the text segment gets executed, in this case the instruction at address 0. And then maybe the next instruction in memory, you already know that there is this sequential execution of instructions and that you have jump instructions, which might influence this sequential order. But this is not relevant here. What is relevant that at some point of time we will have entered function main. That means we will begin with the execution of the first instruction function main. And here it also doesn't matter whether some underscore start function actually was called first or not. What is relevant that before the execution of this first instruction in function main starts, some part of the memory, some memory block, actually needs to be reserved for this function. So that function main does have a memory location for all its local variables. And for that, we can think of a block in memory, for example here, that function main can use for its local variables. Now, the disadvantage of using a block here right after the BSS segment is actually that the address of this block then would depend on the size of the program. For example, the size of the text segment. So it would depend on how many functions you have. And on a lower level, this is actually inconvenient. You always want to have kind of the same address where this memory block begins. And for that, it's actually more convenient to use a block at the end of the memory. Because then the address where this block begins just depends on the size of this block. Basically, you can subtract from the size of the memory the size of this block, and with that you get this address here. Now this block in memory then will be called the stack frame for function main. Let's write this down. This would be the stack frame for the call of function main. And in here we have the memory location for this variable C in this case. And it's called a stack, as you will see, because when we then call function foo also needs some block in memory for its parameter y, and this block then would go here. So you have a stack which grows from right to left. So this would be the stack for function foo, and here we would have the local variable y. Then we call function bar, which means the control flow continues here, and that means we also need some block in memory for its parameter, for parameter x, and this would be the stack frame for function bar. Now actually in this stack frames a bit more than just the local variables are stored, also return addresses, but this is also not relevant here. Let's also consider what happens when we leave a function. When we return a function and continue here after the function call of bar, it simply means that this memory region is no longer valid. It doesn't mean that it's overwritten with zeros, it just means that another function call could use this part of the memory. Also, when we then return to function main after this call to function foo, it also means this just gets invalidated. So you see the stack grows from right to left, and when you leave a function, you simply release some part of the memory. And that's the technical background that you need to understand to see that a large part of the memory still will be unused. We still have here, in this case, almost 4 GB if the memory size is 4 GB, which is neither used for the program, for the instructions and the data, and which also will not be used for the function calls. And this region is called the heap. And this region can be used for data that can be dynamically allocated. And this is what I want to show you next. In this example, I use the two most important functions for dynamic memory management, function malloc and function free. Both of them are implemented in the standard library, and both of them are declared in the corresponding header file for the standard library. Now, to give you an idea how these two functions can be used for this dynamic memory allocation and what this actually means, let's go through this example by following the control flow. So when we enter function main, we have these two memory locations for these local variables on the stack. That means somewhere here we have the stack frame for function main, and within here we have a memory location for the local variable x and for the local variable y. Both of these local variables are not initialized. That means now they still have some undefined initial value. And then we call here function malloc, and here we begin with the arguments that we pass to function malloc, actually just one argument, the value 4. And this means that on the heap, that means in this region which is not used for the program, its global variables or the local variables, this function reserves 4 bytes. So that means we have here a block of 4 bytes. And what function malloc returns is a pointer to the beginning of this block. That means it points to the left edge of this block. Now, what does it mean to reserve or to allocate a block in memory on the heap? It means that if we now call malloc again, we will get another pointer to another block with 4 bytes, and this block will not overlap with this block. That means we get, for example, a pointer to this block in memory, also with the size of 4 bytes. And afterwards, after this assignment, y will point to this block. That's actually almost it. Of course, you see here a few things which are not good practice. For example, things work here that we now have a pointer to integer because on my machine, an integer has the size of 4 bytes. But you know that this is actually platform dependent, and actually we should use something like sizeof to do things right. We will deal with that in the exercises, but also there will be an additional video about dynamic memory. Here I just want to go through the basics. Now let's continue with the control flow. Here I write the value 42 to the end of the pointer x. That means I write to here the value 42. And then to the end of pointer y, the value 13. So to here. Then here with the next two statements, I print these values, the values at the end of pointer x, the value at the end of pointer y, and that's why you see this output. And then I'm a nice guy. I also release the resources that I allocated. For example, here I call function free, which means that now a subsequent call to function malloc could use this block for another memory allocation. And I also release the block here. And then I leave function main. Now, releasing memory when you no longer need it, when you do dynamic memory management, is actually something important, because otherwise you have something called memory leaks. You sooner or later run out of memory. Certainly not in this case, and certainly not in a case where you anyway, after you leave the function, also terminate the program. But it's certainly also in this case a good practice. But also this is a topic for the exercises and another video. What I want to show you in the last example is how certain things can go wrong if you do management by yourself. Let's again walk through the program, through the control flow. We again have this stack frame for function main with these two local variables. So a memory location for x, a memory location for y, uninitialized. Then we call in this assignment again function malloc with argument 4. That means we get a pointer to a block with 4 bytes. And then we release this block, which simply means that a subsequent call of malloc can reuse this memory location for another allocation. And this exactly happened in my case when I execute the next assignment. Then in this case, malloc was using the same memory location and was returning the same address as before. But this is undefined behavior. Malloc also could return a pointer to this memory location, which is a dangerous thing. Once you have released memory, you never should access it. But in this example, I actually did that. You see that I'm assigning here values to the end of the pointer. First, I assign to the end of the pointer 42, So I was writing this into this box, and then to the end of pointer y, which points in this case obviously to the same memory location, I was writing the value 13. So I was overwriting this with 13. And that means after these two assignments, I was printing out the same value when I was looking at the end of pointer x and the end of pointer y. But again, highly undefined behavior. Okay, but that's it for this video. As I said before, more in the exercises, and most of all, there will be another video.